but this year in March they've made it an online conference.
Oh,
And
okay.
they moved it to March with the hope that it can be an on-site conference, but then they decided to make it an online one.
Mm.
Right. Then Clio is in May. That
Okay.
also we have to see what will happen.
Mm.
Yeah. So realistically, I think 2021 also not much travel. I think
Yeah.
only we have to see only next 2022.
Mm.
Yeah.
Do you collaborate much with other people in your department or outside the department primarily?
In my department, I do collaborate. I don't know if you know Kaushik Majumdar. He does work on 2D materials and all that. So we collaborate with him, and also I have some collaboration with faculty in Sense and Physics
Uh-huh.
department as well,
Okay.
and one collaboration with biology as well. We have a nonlinear microscopy system in the lab. So
Mm.
any interesting samples we get is an opportunity to collaborate. Yeah.
Okay. Mm.
Yeah.
Good, good. Yeah.
Yeah. Okay. Apparently, the streaming has started in YouTube. They have set it up.
Okay.
So yeah. Yeah.
Tell me when I should turn on the video and all that. Yeah.
Okay. Yeah. There's still time. Another 5 minutes is there. Yeah.
Okay.
Okay, so we can get started now. It's already 3 minutes past 4. I think few more people will join as we go along. Good afternoon, everyone. I would like to invite you to this EC webinar. So today's speaker is Dr. Arun Kumar Sridharan, and he is a senior engineer at General Electric here in Bangalore. And he has been working in GE since 2013, and he has been working in the area of laser-based and real-time gas and temperature sensors for some of GE's gas turbine and coal boiler products. And he also has a lot of experience working in optics. And before joining GE, he was working in Lawrence Livermore National Labs in the US, where he has been conducting research in the area of fiber lasers, amplifiers, and also metrology products. And before that, he completed his MS and Ph.D. from Stanford University, working with Professor Robert Byer in 2006, where he has worked in the area of solid-state lasers, nonlinear optics, and so on. Right. And in 2013, he was recognized as one of the top 100 innovators of the year as part of this R&D 100 magazine as well. Right. So with that introduction, I would hand over to Arun, and I will share the screen. And one request for all the attendees is to please put your mic on mute. And then if there are any questions, you can either raise your hand or you can type in the chat box, and then we'll take it at the end of the presentation. Okay, Arun, it's all yours. Let me share the screen very quickly. Right.
Okay, thank you very much. Thank you for the introduction, Varun. Good afternoon, everyone. So today I would like to talk about some of the challenges in renewable energy and the evolving role of conventional fossil fuel-based energy sources. I'm part of a small group called the Emerging Technologies Group in GE Power in Bangalore. And much of the work that I'm going to be talking about today was done in collaboration with my colleague Samir Vartak and several colleagues in the power division and the research division of GE over the years. So with that background, I'd like to get started. I want to first give a brief review of the physics of climate change in order to motivate, next slide, to motivate the essential objectives of innovation in the energy sector. The picture on this slide shows what happens when the sun rays strike the earth. On the way to the earth, some of the photons are absorbed by CO2 molecules in the atmosphere. Other photons actually reach the earth and are reflected from it or are radiated after absorption by the earth. A large fraction of photons are again absorbed by the molecules in the atmosphere, and very few make it back to space. Absorption of light by molecules leads to gradual warming of the atmosphere. This is essentially what is known as the greenhouse effect. This is best illustrated by the plot on the upper right. It shows the change in the average global temperature over the last 180 years. You can see that before the rapid rise in industrialization, the temperature was steady. However, gradually over the last 100 years, the temperature has crept up. The increase in temperature is causing the melting of ice in the ice caps, changes in precipitation patterns, human health, agriculture, and testing the survivability of many birds and animals. So next slide. So to basically reduce global warming, we need to reduce the amount of CO2 in the atmosphere. This plot on the left shows the various contributors to global CO2 levels. Industry contributes about 26%, buildings 9%, transportation is 25%, and the power generation sector is about 41%. And this corresponds to about 13.7 gigatons of CO2 annually from the power generation sector. The total electricity generation on a global level is about 27,000 terawatt hours. So in spite of all of this electricity being generated, there are about 770 million people were without power. And therefore, if we look forward into the future, we can see that the electricity demand will continue to increase as all the people without electrical power today start getting them in the future. Next slide. So in this plot, I want to sort of compare the levelized cost of electricity over the years for different power generation technologies. The levelized cost of electricity is basically the cost of producing, it's the cost of the production of power by a power plant divided by the amount of electricity that it is expected to produce over its lifetime. This cost does not include government subsidies. As a reference, in this plot, you can see that the combined cycle gas turbine power plants are represented by a solid blue line, and the coal-fired power plants are represented by a solid black line. The cost of, over the last 10 years, the cost of both wind and solar power plants has come down considerably due to technologies improvements and the scale of manufacturing. As solar panel manufacturing ramps up in volume, its per unit cost comes down. And in the case of wind turbines, in addition to quantity, the larger you build a wind turbine, the more power it can produce relative to its incremental cost. So what you find is that onshore wind has become cost competitive with respect to coal since the year 2016, and it's now cost competitive against combined cycle plants as well. The solar photovoltaic power is cost competitive with coal and gas turbine power plants today. But you can also observe that offshore wind is more expensive, but it is becoming more and more cost competitive, and it might approach the costs of coal by the year 2025. The main reason offshore wind is more expensive than onshore wind is related to its location. Considering that it's offshore, wind turbines need a large structure either to anchor them to the seabed or to support them through a floating platform. This platform should be able to survive sea storms, and so it needs to be pretty rugged. Additionally, if you look into the needs of offshore wind, you realize that you need undersea power cables, and you need to be able to connect them to the onshore power grids. All of this is quite expensive, as it costs a lot of money to get crews to these platforms to do all the connections and then bring them back. And whenever there are maintenance events, you need to be able to do them in a do them quickly, as the costs add up quite quickly. Now, that's what I wanted to mention about wind. If you look at solar, there is another technology called concentrated solar power. It is also expected to be quite expensive. Again, costs are coming down, and then there are some technical problems in this field as well, because some of the mirrors that are used to focus the sun's energy on a particular spot to produce heat, some of those mirrors tend to get dusty, and so additional amount of effort is needed to keep those clean. And you also need to have additional tracking equipment to basically track the solar rays and focus them into the single spot where you want to heat up some sort of material and store the sun's energy in that way. So in summary, both onshore wind and photovoltaic solar are already cost competitive with respect to traditional thermal power plants. These technologies are pretty much here to stay and are likely to become even more competitive in the future. More and more of the total power that is produced in the grid and delivered into the grid will come from these technologies in the future. And this is something that we are observing today, where most of the new installations are coming from the renewable space. The only one problem that these technologies have is that they are not dispatchable. So because you can't predict when the sun will shine and when the wind will blow, you can't predict when exactly and how much power you'll be able to generate from these sources. And so you will not be able to generate power arbitrarily on demand. Next slide. So that is the downside of the renewable sources. So before we kind of examine the typical scenario for solar and wind production, let us look at a typical day sometime in the future when the power grid is dominated by wind and solar power. The power, as you can see on this plot, the power demand over the day rises and it peaks at noon and it diminishes at night as people go to sleep. Next slide. If we add to this plot a fictional but representative supply of power from solar photovoltaic power plant, you can see that at night there is no power produced. Power production rises as the sun rises and peaks sometime just after noon when the sun is at its highest. In this example, when a storm passes over land in the afternoon, there's a small dip in the power that is produced from the solar plant. And the solar power again drops back down to zero in the evening hours. Now, if on top of this solar plot, we add a fictional but probably representative plot of the amount of power supplied by wind, which is shown in blue, we find that again, as the wind again picks up during the daytime and it dies down again at night. Next slide. So what you will notice from this plot is that there is a gap between how much power is available from renewables and the demand. So what you would ideally like to do is to take the excess power produced between noon and sunset and charge an energy storage device. We could then use that energy storage device to provide additional power later in the evening. When there is insufficient power available in the morning, we would need to take power from some sort of longer term storage. For instance, if over the last several weeks more power was produced than needed on any given day, you could use that excess power to store some sort of longer term storage device. And then when that power is needed, you could extract it. Or you could essentially use other dispatchable power plants at a time when that power is required. Next slide. So today's electrical grid actually demands energy storage devices that can supply different amounts of power over different discharge times. For example, voltage and frequency regulation demands are on short time scales on the order of minutes, seconds to minutes, whereas raw grid scale power has a significant component on the seasonal time scale. Next slide. Fortunately, depending on the geography and the societal needs, there is also an annual variation in the power supply and demand. If we take a country like Germany as an example, the power demand is typically lower during the summer months and higher during the winter months. This is the case because air conditioning is rarely used and in the summer, and significant house heating is required during the winter. This scenario would be different in different countries, and so you would have some sort of a plot like this where there's a seasonal mismatch between supply and demand. Now, so what you would like to do, next slide, is to basically store the excess power in one of the seasons. In this case, it would be the summer, and then use that power during the winter when it is required, when there is less supply available from renewable sources. Next slide. In order to kind of assess the different energy storage technologies and the efficiencies, the World Energy Council has produced a very nice chart that compares the different energy storage technologies. On the x-axis of this plot, you can see the potential energy storage capacity of each technology. And on the y-axis, you can see the discharge time rated power. Okay, discharge basically, discharge. I mean, it goes from 1 second to 1 year. On what time scale do you need to discharge that, right? The technologies, if you look in the bottom left of this chart, you see that technologies like supercapacitors and flywheels can only store small amounts of power for very short periods of time, whereas technologies on the upper right of the chart can store large amounts of power for longer periods of time. An estimate of the range and round-trip efficiency for each technology is also given. So that is the percentage numbers that you see next to each of the bubbles. The round-trip efficiency is basically an indicator of the amount of power that can be supplied from the amount of power that has been stored. Okay? So, for example, if you had a round-trip efficiency of 90%, and when you stored 100 megawatt hours of power, one could get back only 90 megawatt hours. When most people think of energy storage, people think of batteries. And indeed, batteries can have a very high round-trip efficiency, almost 100%. So we're getting around 95% or so for lithium-ion. Lithium-ion batteries are probably the most mature technology in terms of battery technologies. But the problem with lithium is that it's a rare mineral, and so the devices are extremely expensive and are not practical for long-term storage at grid level. They are used today, though, for day-night cycles, and they make up a very small fraction of the grid storage needs of society today. This is not to say that they may not reach that point in the future, but today, lithium-ion is a minor player in the grid storage field. Flow batteries, on the other hand, often can potentially offer a less expensive solution for longer-term storage. But they also have lower round-trip efficiencies today. So there's a lot of research being done in this field, and this is a very dynamic field, and you can expect a lot of improvements in this field over years. So, but this is where the technology stands today. So, so as far as if you wanted to know what are the promising technologies for long-term energy storage, those are the numbers on the far right today. So there are probably 3 or 4 technologies that are most promising today, and so I'd like to maybe talk a little bit more about those. That's not to say that the batteries will not improve over time, but today this is the situation. So the first promising long-term storage technology is thermal storage, where electricity is used to directly heat a thermal storage device to store excess power. If this heat can be used to directly offset electricity demand, such as to provide hot water for heating buildings, then this form of energy storage can be very efficient with round-trip efficiencies as high as 90%. So the net efficiencies will be around 35 to 50%, but the round-trip efficiency of just the thermal storage itself can be closer to 90%. However, if the heat needs to be turned back into electricity through a heat cycle, for example, by producing steam or driving a steam turbine, then the round-trip efficiency comes down to 35 to 50%. So over time, thermal storage will lose its heat, and according to the World Energy Council, this sort of technology is suitable for longer storage times than batteries, but not as long as other technologies that I'm going to talk about now. Another interesting technology is called LAES, that is liquefied air energy storage. In this technology, electricity is used to liquefy air. Energy is then recovered when the air is reheated and expanded. So that expanded air goes through a turbine, and then power is produced in the conventional way. So that is LAES. Another technology is called CAES. So that is called compressed air energy storage. In this technology, electricity is used to compress air energy is recovered again when the compressed air is expanded into a turbine. When the air is compressed, it also heats up. So if the air stored in a vessel loses this heat over time, the round-trip efficiency will be lower. This is especially a problem for longer-term storage. So that is the situation with the CAES technology, that is compressed air storage. Another very conventional approach to long-term storage is pumped hydro. Pumped hydro is a very mature technology, and it has been around for decades. And in fact, the majority of grid-level energy storage today is in the form of pumped hydro. This is basically where you have water across 2 different elevations. When you need to store power, you basically pump water up to a certain height. And then when you need to discharge power and sort of bring power back into the grid, you basically let that water fall, and the loss in gravitational potential energy is then used to drive a turbine to do work and to produce electrical power. So of all the long-term energy storage devices that are available today, this one is probably the best. But the limitation with this technology is that many of the geographically well-suited areas for this technology have already been used up. So it's not clear how well it can scale or how well it can scale in the future. How much more resources you have, how many more places in Earth where you can do this and apply it well. So these are the 3 or 4 technologies that are, I think, currently already being used to some extent. But there is one final technology that is called power to gas that I want to talk about. And this is where gas turbines and GE's technologies are seen to play a role. Power to gas in its simplest and cleanest form is where excess power from renewable sources is used to produce hydrogen from water using electrolysis. The hydrogen can be stored for very long periods of time, and it is recovered again and the energy is recovered again by burning hydrogen in a combined cycle or a simple cycle power plant. That is basically, since there is no carbon when you are burning, that is in the turbine, in the combustor, you are basically not producing any CO2. You're basically only combusting hydrogen. So this is a technology that's is promising, but a lot of work needs to be done in this field in order to make the process of electrolysis very efficient, the storage of hydrogen efficient and safe, and the transportation of hydrogen efficient and safe as well. So there's a lot of work that needs to be done. And there is also another way in which you can do power to gas, and that is to use the excess hydrogen that is produced to generate something called SNG, that is called synthetic natural gas. And so when you combine hydrogen molecules and a little bit of carbon, you can basically make methane, which is in an artificial way, and burn that. But when you do that, what's happening is that you're essentially putting carbon back into the combustion chamber and producing CO2. So it's not so favorable, but it is favorable from the point of view of energy density. And this is something that I'll discuss a little bit more. Natural gas is more energy dense, whereas hydrogen is not that dense. And so you really need a lot more volume of hydrogen for a particular amount of heat release from the combustion chamber. So next slide. Right. So now that I've talked to you a little bit about energy storage technologies and how they are going to play a role in the future, I want to discuss a little bit more about some of the transforming trends that are happening in turbines. As you all might already know, a turbine is basically a rotary engine that extracts energy from some sort of a fluid that is flowing through it. Right. So you have a generator that is connected to the turbine, which produces power when fluid flows through it. What we see is that gas or steam turbines will increasingly play a secondary role in power generation in the future. And they will do this by extracting power from energy storage technologies. But that is in the longer term. In the nearer term, natural gas turbines will continue to provide a significant percentage of global electricity for the next 2 to 3 decades. And so that is because a significant portion of the current electricity production is already based on natural gas and coal, and so that will continue. But these technologies will decarbonize. So there will be ways in which society tries to reduce the CO2 emissions from these conventional power plants. So if you want to decarbonize, you can either do a few different things. You can do some things before the combustion process, and that's shown in the plot below, where you can either burn hydrogen, you can burn synthetic methane, ammonia, or biofuels. So these are the different things that you can do that are part of if you bring in these fuels, then those are the things that you can do as part of the combustion process itself to ensure that the output is having no CO2 at all. Now, if you already have some sort of natural gas in the combustion and you want to do some cleanup at the end, you can also do things like carbon capture and use oxy-fuel cycles. So these are some things that you can do at the tail end in order to take care of the pollution that you're generating. But if you want to basically avoid the pollution in the first place, you can go to some of these alternative fuels. Next slide. GE has actually a lot of experience working with hydrogen. There were research programs starting in the 1990s working with hydrogen. If you look, we're now on slide 18. No. Yeah. Let's see here. Yeah, we're on slide 13. Sorry. So GE has a lot of experience in hydrogen and other low BTU fuels. As you can see, there have been installations both in the US, Europe, and in Asia over the last several decades, where the technology of burning hydrogen in at least smaller, in increasingly greater amounts, has been tried and tested in a commercial sense. So this is not a new thing to GE. There are, if you look in the next slide, slide 14, so there are a few different fairly serious projects going on with hydrogen-based gas turbines right now, where you have one project which is burning hydrogen fuel up to a very high amount, somewhere around 70 to 95%. There's another project going on where hydrogen and natural gas are being combined. That's shown in the middle picture here. And it is a target for GE to achieve a 100% hydrogen-based turbine by the year 2030. So that is shown in the in the right-hand side. So that is at Long Ridge Energy Power Plant in the USA. So the target is, starting this year, in the next 10 years, GE is going to increasingly add more and more hydrogen to its natural gas power plants and get the power plants turbines ready for burning alternative fuels. So this is GE's strategy to decarbonize. To better understand, next slide, to better understand the potential of hydrogen-based power generation and some of its challenges, we need to dig a little bit deeper into its material properties. The table shown here compares hydrogen's properties with methane, which is the prime component of natural gas, and ammonia. So we have, if you see on the top, you have a comparison of methane, hydrogen, and ammonia. And you can see that hydrogen's combustion properties basically involve, or rather include, very wide flammability limits, much higher reaction rates, preferential diffusion, and higher flame temperatures. These material properties lead to very short auto-ignition times and a very high flame speed. So as a result of these things, the combustion that happens in a hydrogen turbine happens very quickly, and it happens before the air and the hydrogen have had time to get fully mixed. Now this can lead to problems like flashback, where you have a flame being generated in the premixer region, and that's a problem because the premixer is not really designed to handle a flame, and so the flame really needs to exist inside the burner or in the cans, or rather, well, inside the combustion chamber. So because the flame, basically the idea is that burning hydrogen is not so simple. You have to handle, be able to design the different cans and the premixers to effectively combine the air and the hydrogen, and you need to find ways in which you can prevent flashback from happening. So there's a lot of research going on right now to figure out how that can be done. So there are people who are already looking at maybe taking some of the exhaust gas and feeding it back into the turbine, back into the combustion chamber to minimize flashback and things like that. So that's that for flashback. One of the facts that you can observe is that the high flame temperature of hydrogen also leads to high NOx formation, because the oxidation of nitrogen is highly and strongly sensitive to temperature. So steps to mitigate this also need to be taken, and active research is underway in this field as well. And again, as I point out in the bottom of the slide, further research is also required in high temperature measurements, pipeline leak inspections, and improved models of combustion dynamics and emissions. So this is a very rich field that will see a lot of progress over the next few years as society tries to find ways to decarbonize the existing gas turbine power plant fleet. So now I want to step back a little bit and try to give you an idea of what GE is doing before we transition into a fully hydrogen economy or an alternative clean fuel economy. We need to still operate with existing gas turbines in as clean a manner as possible. To help with this, GE has been making simple cycle gas turbines to operate as peaker units that are turned on and off to compensate for fluctuations in the amount of power that is available from renewables into the grid. These peaker unit gas turbines are often followed by, as shown in this figure. We're now on slide 16. Let's see here. Let's make sure that I'm on slide 16. Yes, we're on slide 16. So in this slide, you can see that you have a picture of a. We're not showing the gas turbine part of it, but we have a hot gas coming from a gas turbine that is going into a duct that then goes through a CO catalyst to reduce CO, and an SCR, which is to reduce NOx, and then the output of that goes through the chimney and into the sky. So the selective catalytic reduction unit involves injection of ammonia, so that ammonia can then react with NO and NO2 molecules to produce harmless nitrogen and water. One of the problems that we see in these simple cycle gas turbines is that during startup, when the temperatures of the SCR have not yet stabilized and have not reached a point where the SCR conversion efficiency is at its most efficient situation, you have a lot of extra NOx that is being released into the atmosphere. So during that startup phase, when the temperatures have not stabilized, you have a lot of extra NOx. And because these power plants are being turned on and off quite often several times a day in order to compensate for renewables, currently you have a lot of extra startup emissions. And this is often a problem in jurisdictions like California, where emission regulations are quite low. So there is really a need for figuring out a way in which you can reduce startup emissions in places like California and other places where we have stringent emission requirements. What GE has done in order to reduce startup emissions in some of these simple cycle gas turbines is to inject water into the combustion chamber itself. What this does is it reduces the temperature and therefore it reduces the NOx. Now, it's very hard to figure out how much water you must inject. And this is where there's a lot of need for advanced sensing technologies that can basically detect the amount of NOx that is there, that is coming out of the turbine, and on a real-time basis, and then use that NOx signal to basically inject just the right amount of water into the turbine, so that you can keep the NOx at the required low levels as required by the regulations. So when you are able to do this and measure the NOx in real time, you can essentially do feedback control of water injection, and you can also use the same signal to do feed forward control of ammonia injection into the SCR to really dampen down the emissions that are going out through the chimney. Next slide. We're on slide 17 now. So the sensor that we built here in Bangalore to measure turbine emissions is based on a cross-stack approach. The gas turbine, so the sensor consists of a transmitter which is attached to one side of a gas turbine duct and a receiver on the other side of the gas turbine duct. The transmitter consists of a number of lasers that are tuned to the absorption wavelength of the different gases of interest. And the receiver has detectors that are able to collect all of the unabsorbed light and convert that into an electrical signal, which is then changed into a concentration value in real time. So the transmitter itself has quantum cascade lasers that emit radiation in the mid-infrared portion of the electromagnetic spectrum. We had to do a lot of high temperature gas spectroscopy to figure out the absorption of the different species at those wavelengths and do 2F by 1F lock-in detection in the receiver in order to really infer small amounts of absorption of the different gases that are going through the gas turbine chamber. So this is the sort of the basic idea and the basic design of our sensor. We deployed this sensor at next slide at a plant in Riverside, California. These are some of the pictures that you can see here. This is so we have, as I mentioned earlier, we have a transmitter and a receiver. The top two pictures show the transmitter platform. We are about 10 meters above the ground. We had to build a platform and install some of the transmitter prototype instrumentation, which is then bolted to the duct through a flange. On the other side of the duct, you have a receiver, which is also bolted. Again, you can see a picture. You can see two pictures of the receiver on the bottom. One is from the ground up, and one is a close-up view from the platform itself. So the receiver is again bolted to the duct and collects all the light that is coming through the gas turbine chamber from the other side. So you have electrical cables that are going down to the control room, where we do advanced and more signal processing in order to back out the concentration information of the gases in real time. That information, that gas concentration information, is then converted into the Ethernet global data communication protocol format, and then pushed out to the Mark 6E controllers that are actually used to control the gas turbine and adjust the water injection appropriately. Next slide. So what are some of the features and applications of this fast sensing technology that we built up here? One of the features of this sensor is that it had improved concentration accuracy compared to some of the other traditional SEMS devices, other sensors that are there, because we are actually getting a line average of the measurement, of the gas concentration measurement, because light is actually going through the entire duct. The duct could be several meters wide, 5, 10, 15 meters wide, depending on the power plant. So you're getting a real average as light travels through the duct. With this, you can do better controls and probably better regulatory reporting as well. The fast time of the response of the sensor allows you to do both gas turbine controls and SCR controls at the same time. It allows for wider operability of the gas turbine and you can operate the gas turbine closer to its limits. And it really gives you rapid insight into gas turbine and SCR performance degradation. Another feature of the sensor is that it reports the different concentrations CO, NO, and NO2 separately. Unlike some of the other SEM sensors where NO and NO2 are combined and it gives you one NOx reading. And it takes a little bit of work to figure out how much of NO you have and how much of NO2 you have. So this is an advantage of our sensor. We were able to work with our collaborators at Stanford University and use their facilities to do some EPA certification tests as well, and showed that the readings of gas concentrations that you get from our sensor are very close and to the reference values, and therefore acceptable for reporting to the EPA. So we showed that as well, and we were able to, in addition to measuring the gas concentrations, we were able to show that by doing some neat spectroscopic tricks, we were able to infer the gas temperature as well in a line averaged way with this sensor. So we were able to process the same data and get the gas temperature as well. So this fast sensing technology is something that I feel will have more and more play in the GE gas turbine fleet as things go forward. It can yield a number of different outcomes for the customer, potentially reduce outages, improve the gas turbine hardware and life, and result in reduced water and ammonia consumption in the power plants. Next slide. So now that I've talked about the what we have done, the research that we have done in helping the aeroderivative power plants, the peaker units, operate in a more flexible way with reduced emissions, I want to talk a little bit about some of the work we have done for the bigger power plants, combined cycle power plants. So these are power plants that emit hundreds of megawatts of power, and they often have two heat cycles. One is you have a primary combustion chamber which produces a hot gas, and the turbine, there's a turbine that's connected to that. There's a generator connected to that turbine which produces power. But that hot gas is then made to impinge upon a bunch of tubes inside what we call a heat recovery steam generator chamber. So these tubes have water flowing through them. And so as the hot gas loses its energy, the water heats up, a steam is produced, and that steam can then drive another steam turbine. Now that steam turbine is again connected to another generator which produces power. So you have two stages of power production in a typical combined cycle power plant. And so in order to optimize and to help these combined cycle power plants operate more flexibly, these power plants are meant to operate at very high megawatt loads and to stay there. But if renewables are coming into the grid more and more, these power plants will now have to operate in a much more flexible way. They'll have to operate at low loads, they'll have to cycle up and down, and so they are operating in a regime that they were not designed for. So in order to optimize these kind of combined cycle power plants, you really need to know the gas turbine exhaust flows, temperatures, and emission levels need to be known very well so that you can design the SCR and optimize the SCR very well. You want to obviously know the gas turbine exhaust temperature very well, because the steam production of steam and the quality of steam that you get depends on the gas turbine exhaust temperature. You also need to achieve the lowest possible NOx emissions for regulatory purposes. Even though you're now in a secondary, even though this power plant is now kind of secondary to renewables, you still need to make sure that it produces the least amount of NOx to stay below the regulatory limits. And you need to do it in a way that basically keeps the turbine from reaching acoustic limits and reaching the flame out limits. So those are all the challenges that you face when you're trying to design and operate a combined cycle power plant in a very different regime, much more flexibly. So So what GE is doing in this field is to work on some a software application called a startup optimizer. The goal of this software is to give to provide a plant level solution to the engine control room to help that customer achieve certain outcomes, right, that he wants. So the customer might want to achieve a certain amount of fuel consumption, to achieve a certain amount of startup time. They may have a certain profit motive. They may have to stay below a certain amount of emissions and to achieve a certain amount of output power. These are the different kind of goals which a customer might have at any given point of time. And so what we want to do is to show a way in which the customer can achieve these, basically teach the customer how they can ramp up the plant in order to achieve their objectives. So the GE has developed a software suite where the user or the control plant, the control room engineer will basically put in his goals. And the software will rely on a number of digital twin models. It'll take in a lot of inputs regarding the plant conditions, and also take in some financial information regarding the cost of fuel and things like that, and some of the other constraints, and basically tell the basically provide a startup path, right, for the control room engineer, so that he can, as in the most optimum way, take the power plant from zero load to the maximum load to achieve his objectives. So this is a software application that I was involved in, and it is now this software application is now helping some of the heavy duty gas turbine customers around the world to achieve a better outcome compared to what they were getting earlier, right, in light of increased renewables and penetration into the grid. So this is an example of one thing that GE is doing using digital technologies in order to help its heavy-duty gas turbine customers operate their plants more flexibly. So next slide. I want to now shift gears a little bit and talk about what GE is doing for its coal-fired power plants. So now we are on slide 22. The coal-fired power plants consist of a coal boiler, followed by a selective catalytic reduction unit to reduce NOx. It is followed by an electrostatic precipitation unit, which is used to reduce the amount of particulate matter that is going through the flue gas. And a typical coal power plant has something called an FGD. What that means is that it is a flue gas desulfurization unit. So it reduces the amount of SOx emissions that are going through the flue gas. So these are the different after treatment systems following the boiler. And in order to optimize all the different systems, you need gas and particulate matter sensors before and after each of these subsystems in order to be able to optimize the plant very well. So one particular project that I was involved in involved the optimization of the boiler. And in order to optimize the boiler performance, what is required was a measurement of CO in real time. And to understand that, I'll illustrate that with a little plot here shown on the left. So now we are on slide 23. The plot on the left basically shows various combustion parameters as a function of the air to fuel ratio. Now, to minimize CO emissions, the boiler is typically operated to the right of the peak efficiency point. Okay, so the peak, you can see that the top curve there is the efficiency curve of the boiler, and to kind of not allow CO emissions to go up very rapidly, the plant is operated a little bit to the right. However, if you are able to get real-time awareness of the CO emissions, then this information could then be used to set the air-fuel ratio closer to its optimum. And when you do that, you can improve the boiler efficiency without really compromising on CO emissions. We actually demonstrated a CO-only version of the fast emission sensor at a GE test boiler facility, and showed that the result achieved results that were that compared very well to the reference sensors on the site. So that's one thing that we have done in terms of using sensors for the optimization of boilers for coal power plants. Another project that we did to help coal plants operate more flexibly involved what we call as ignition technologies. If you go to slide 24, what you will see is that oil burners, most of the power plants that run, because there's so much renewable power in the grid, you need to operate coal power plants at lower and lower loads. And when you operate a coal power plant at low loads, the flame can die out. In order to make sure that the flame doesn't die out, you need a pilot flame. And that pilot flame is generated by burning oil. Now, ideally, you'd like to get rid of oil because they have high operational expenses if the coal plant is operated at part load for a long time. And they also contain a lot of sulfur, which leads to a lot of corrosion issues. So we want to be able to get rid of oil burners. And so we have come up with some novel technologies for getting rid of non-oil, to basically build a non-oil igniter that achieves a flame at a lower cost. And because no oil is there is no emissions. And it allows, and the end result is that you can have more flexible operation of the coal power plant. So one novel technology that we invented last year for igniting and producing a pilot flame involved lasers. And we used, the basic idea behind this technology is that we use the coal that is already available and flowing inside a coal boiler. And we use light from a very high power continuous wave laser. The light from the high power CW laser is basically getting absorbed by the coal particles. The particles will volatilize and ignite. The energy that is released will get absorbed by other coal particles. They will heat up and they will ignite. And so this process continues, and it happens, and eventually you get a flame. So this flame then goes into the boiler, and it provides a pilot flame, and it basically ensures that the flame of the coal boiler doesn't die out as the coal plant is operated at lower and lower loads. So this was a very promising effort, and we showed this quite successfully in the laboratory in a test facility in the US last year.
Arun, just a quick time check. We have 5 minutes left, I think.
Sure. I'll wrap up. Just 2 minutes. So just to review, we are in slide 26. I guess in summary, I'd like to state that reducing greenhouse gas emissions is very important, and that means reducing CO2. Reducing CO2 means finding ways in which to decarbonize the existing fossil fuel-based power plants and moving to renewable energy sources. We believe that dramatic cost reductions in renewable energy technology and energy storage will eventually enable a clean energy future. There are a number of metrics for evaluating energy storage technologies. It's a very complex field, actually. You can see on the right side of this chart, there are a number of factors that come into play when you want to figure out which energy storage technology to choose. You need to be safe. You need to have good round trip efficiency. It has to have the required ramp rate for your application, power, energy density, cycle life, calendar life, and so on and so forth. So there are a lot of metrics that need to be met simultaneously. And different applications require a different amount of emphasis on these different metrics. And so you will need different storage technologies. And so the technology development must take into account the business use and a rapidly evolving market, and also a lot of the geopolitical risks that are there. So, so that is the sort of how we see the field of energy. Next slide. This is my last slide. Just wanted to say that as renewables and energy storage technologies play an increasingly important role in the building up of new power into the grid, the existing coal and gas turbines still have a role to play. It's going to take a significant amount of time to really get rid of the old gas turbines completely from society. So what really is going to happen is that the existing gas turbine and the coal plants we'll have to figure out ways to operate them in a more cleaner way, and that means trying to find alternative cleaner fuels, and that means perhaps doing some sort of carbon capture on the tail end. But the process of decarbonizing the existing fossil fuel fleet has to go side by side with building up the capacity in the renewables, because ultimately you need grid level storage for the society at large, and that amount of raw grid level power is currently only available from the existing coal and gas power plants. So we have to find a way to decarbonize the existing fleet with advanced sensors and emission mitigation technologies, as well as advanced fuels and carbon capture, while the renewables and energy storage takes off. So that's it. Thank you.
Thanks, Arun, for the interesting talk. One second. Let me quickly check the chat box if there are any questions. So if there are any questions, please post it in the chat box, or you can also raise your hand and ask the question to Arun. So one question I have, you had mentioned the laser-based sensors, right, which do this F2F detection. So what kind of temperature and pressure do these laser beams go through, and do you need any adaptive optics or something to compensate for the beam walk-off or any aberrations in the beam?
That's a good question. The pressures are not very high because this is at the gas turbine exit. The pressures of the gas are close to 1 atmosphere. The pressures inside the combustor are very high, but once the gas leaves the turbine, the pressures are not that high. So you don't really need to deal with aberrations that are because of pressure stratification of the pressure in the duct. But what you do have is some sort of thermal changes in the walls of the duct. The walls tend to expand a little bit as the gas turbine heats up. The mirrors, the windows through which you send the light, they will heat up. And so you need to employ some sort of a technology to make sure that the light from the transmitter remains focused on the detector on the other end. And the detector is, several meters away, 5, 10, 15 meters away, depending on the power plant. In order to make sure that the transmitter and the receiver are well aligned, we employ something called an auto aligner technology, which involves actuated mirrors, which basically control the positioning of the beam in response to changes in either in the wall itself or due to temperature stratification of the duct. So we have mirrors that are actuated by voltages, and we do active control of the laser light on the detector to ensure that we get a signal throughout the day. But yeah, it's a good point. Yeah.
And when you have multiple sensors, is there any preferred communication format, or what are the interesting open problems for an EC engineer in such kind of energy plants?
I think the communication, a lot of the signal processing that we do is we do a lot of signal processing of the signal. One of the interesting challenges could be, currently we do signal processing at the ground. We send the raw voltages from the receiver. We do some pre-processing on the wall itself, but we do further processing using LabVIEW programs at the control room. The communication protocols that we use are EGD, Ethernet Global Data. So that is the protocol that's required to be that's used by the Mach 6E controller of the GE gas turbine. So all the concentration data that we have needs to be converted into that protocol in order to be communicated. And so different gas turbines use different communication protocols. Some might use EGD, some might use Modbus, some might use DNP3 communication protocols. So there are different communication protocols, and your software needs to be able to send the data. So you need adapter software that can take that data from the sensor signal processing hardware and push it out to the different control rooms that might be there. One of the I think challenges from a sensor construction point of view is how do you handle vibrations? How do you handle thermal drift of the background signal? Because the windows through which you're sending light, they heat up, and so the background signal also changes. You also have a lot of black body emission from the hot gas that's going through the duct. So that black body emission is also being collected by your receiver. So you need to, even though the laser light is modulated and demodulated on the other end, you do have a little bit of that background signal coming through, and so you need to be able to differentiate between light from your laser and light from some of the other sources. You need to make sure that the laser light itself remains focused on the receiver and basically be able to handle, do better background subtraction so that you can get very sensitive gas concentration information, right? So you need to be able to measure very low concentrations, ppm, sub ppm, and things like that. So those are some of the sensor related challenges. One of the the speeds, possibly one of the issues that you could look at from an electrical communication engineer point of view is to see how you can maybe reduce some of the electromagnetic interference that could be there from the gas turbine itself on the sensor hardware. So that's an area where some work could be done.
Okay.
Yeah. So.
Okay. Very good. So looks like there are no other questions. So we'll thank Arun once more for an interesting talk, giving us an overview of how energy turbines work and what are the open questions and sensors and things like that. And I would also like to thank all the audience for attending this talk. And we hope you will join us for the next EC webinar in the middle of January as well. Right. Okay, so thank you very much and have a good evening. And thank you, Arun, for an interesting talk.
Yes. Yeah, thank you very much for inviting me, Arun. And,
yeah, no problem. Yeah, okay. Thank you. And we will see you again later. Okay, thank you.